Hello friends, welcome to the next lecture of GC eConnect series of online lectures. We are dealing with losses in prestress. Let's go ahead with the problems. So in the next problem we have a post tension beam of 12-meter length. A cable is laid symmetrically with its central 6-meter length horizontal and the two straight end portions sloping up at an angle of 0.075. So the profile given in the example is trapezoidal with the central portion of 6 meters flat and remaining 3 meters portion on each side at an angle of 0.075. Okay, so now the cable is tensioned by jacking at one end and anchored at the remote end, means jacking is taking place only at one end in this case. At the jacking end, the stress, that is the initial applied pre-stress, is 1040 Newton per mm square. The wobble coefficient may be assumed as 0.04 per meter. Okay, see the unit here, 0.04 per meter. We have to calculate the stress in cable at the remote end and the 2 points where alignment of the cable changes. Assume the friction coefficient between cable and duct of 0.4, and we also got to find the percentage of loss between the jacking end and the anchor end. So this example is purely based on losses due to friction. Here the effect of the friction between the cable and the duct is also considered, as well as the wobble effect is also considered. The angle is given as 0.075. Let's start with the solution. Okay, so we have drawn a schematic diagram. The total length is 12 meters. The central 6 meter portion is flat, that is BC, and AB and CD are the inclined portions. Okay, so let us say that our end A is the end where jacking is done and end D is the far end. So we got to move from A towards D, that is portion AB, BC, CD. Okay, so let's start writing down the given data. Slope is 0.075, K value is given as 0.004, stress at the jacking end, that is A, which is also the initial applied stress, P0 is equal to 1040 Newton per mm square. So now let us analyze this example part by part. So first part under consideration is AB, which is sloping. Therefore loss of stress between AB. Now at end A we are applying the initial stress 1040. As we move from A to D, what losses takes place we have to find in this example. So firstly in section AB, the loss due to loss of stress between AB can be obtained by the formula P0 into bracket mu alpha plus Kx, where P0 is the initial stress, mu value is given into into alpha 0.075, which is also given, plus 0.004, which is the K value, into 3. Now here x is equal to 3 because we are taking the first span, that is AB, which is 3 meters. So we get the stress at the first kink. Kink means it's a change point or where the direction is changing, that is point B. We get the stress at, firstly we get the loss as 44, then the stress at point B is initial applied stress minus the loss, that is 44. So we get the answer of 996. Therefore see here friends, at A the stress was 1040. Now as we have come to the B point, the stress has dropped down to 996. Now let us go for the section BC. Now BC, it is a flat section, hence there is no need of alpha because alpha is equal to 0 here as the line is flat. So the loss can be estimated as P0 into Kx. Now here at the initial stress is the stress which is at point B and not which is at point A. So we get the stress as 996 into bracket K is 0.004, X is the length. BC span length is 6 meters. Therefore, calculating, we get the answer as 24. Now, let's come to the second kink, that is the second change point, which is at C. Now, as CD is also a sloping line, angle is the same as 0.075. Therefore, losses in this segment will be same as that in the segment AB, which is 44 Newton per mm square. We need not again calculate it, we can take it as we have calculated it earlier. Therefore, now the stress at D, okay, what happens to stress at D is it reduces. So our previous stress was stress at point C, okay, in the span BC, which had come out to be 972. 972 minus 44 gives us 928 Newton per mm square. So as we started from A with a stress of 1040, it dropped by 44 to 996 at point B. Further again it dropped by 24, it became 972 at point C, and when we reached point D, that stress again dropped to a value of 928. So if we compare with the initial stress, the total loss of stress is equal to 112 Newton per mm square when we start from the jacking end to the far end. Therefore, percentage of loss will be total loss divided by applied stress into 100, that equal to 10.8%. Okay, so this was a bit different example where we had to calculate the loss at each point, and finally we got the loss at the farmost end, that is the point D. Okay, so just this is a very simple example actually, but you need to understand the given data and the problem properly. So again, next example, which is an easier one. Here we have a beam which is 300 by 600. The area of steel is given as 250 mm square and located at a constant eccentricity of 100 mm. That means the cables are straight. Initial prestress is given as 1050 Newton per mm square and span is 10.5. We need to compute the losses using the given data. If the beam is pre-tensioned, second case the beam is post-tension. So this is a very good example. If you become perfect with this example, you will be able to solve all the losses, because here maximum of the losses for both pre-tensioned as well as post-tensioned are covered in this example. So the required data is given. So let's come to the solution. Firstly, as stress is given, let us calculate the pre-stressing force, that is stress into the area of steel. So guys, don't make a mistake here, don't take concrete area, because the stress is related with steel only. Okay, pre-stress is applied in steel, not in concrete. So P is equal to 1050 into area of steel, which is given. We get an answer of 262,500 Newton. Then area of the section, or if you want you can name this as AC, that is area of concrete, 300 by 600, which comes out to be 180000 mm square. Then next, modular ratio is 6. So taking this data, we can go for the calculations. So I value is calculated. Next, first step of our calculation will be calculation of FC, that is stress in concrete at the level of steel. We know the formula, that is P by A plus P into E by I multiplied by E again. Okay, so substituting all the values, we get the stress in concrete at the level of steel, that is FC, or sigma c is equal to 1.944 Newton per mm square. Now let's compute the losses. Here the losses are given in the table format, which becomes very easy for calculation. So first loss is elastic deformation. Nicely equation is also written, that is m into Fc, which is modular ratio into Fc. So for pre-tensioned it is 6 into Fc we have calculated as 1.944. Hence we get the loss as 11.664. In case of post-tensioned, as they have not mentioned number of tendons and whether they are stressed individually or separately, we'll assume that a single tendon and it is stretched, so there are no issues of any losses due to elastic deformation, hence it is nil. Second case, relaxation is given as 2.5%, which is for both pre as well as post tension. So therefore 2.5% of initial stress, initial applied stress, that is 2.5 into 1050, which comes out to be 26.25 Newton per mm square in both the cases. Next, creep loss. Okay, creep coefficient is given, which can be used. Only thing to note is in pre-tension and post-tension values are differently mentioned, so don't make a mistake. One is 40 into 10 raised to minus 6, whereas other is 20 into 10 raised to minus 6. Multiplied by the initial stress which we found out, 1.944 into epsilon s. So this is a very easy calculation. You get the answers for loss due to creep of concrete. Then comes loss due to shrinkage. Again the factors are different. Epsilon s is different in both the cases. One is 300 into 10 raised to 6, other is 200 into 10 raised to 6. So epsilon sc multiplied by elasticity of steel gives you the shrinkage losses in concrete, both in pre-tension as well as post-tension. Friction loss. In pre-tension there is no friction loss, whereas in post-tension we get the friction loss by our formula Fs is Fs into K into X. Okay, so Fs we are writing, that is the initial stress, into K value is given 0.0015 into X, which is the entire length of the beam. Then next we are finding loss due to anchorage slip, which is not occurring in pre-tension members, and in post-tension members it is given by epsilon s into delta by L, where delta is the creep which is given data. It comes out to be 30. So when we add up all, in pre-tension case we are getting the total losses as 117.243, whereas in post-tension we are getting the losses as 122.944. Hence we can calculate the percentage, that is the loss divided by original stress into 100. We find that in pre-tension beam the loss is 11.1, whereas in post-tension the loss is 11.7. So approximately here we are getting for this given data, as the span is up to 10 meters, the losses are nearly remaining the same. So this is your second example. So again I am stressing that this example is very easy, and this gives you the entire picture of all the losses, both in case of pre-tensioned as well as post-tensioned members. Let's come to the last example of the day. I have selected this example because again something different is there in this. Okay, here we have a concrete beam AB of 20 meters, which is post-tensioned and carries an initial stress of 1000 Newton per mm square at the jacking end A. The cable is parabolic between the supports AB and is concentric at the supports with an eccentricity of 400 at the center span. The coefficient of friction between the duct and the cable is given as 0.35, and wave effect coefficient is given as 0.15 for 100 meters. Now see the given data, directly you cannot take 0.15, it is 0.15 per 100 meters. Therefore for 1 meter, how much? 0.15 divided by 100. So here there is a possibility of you all making a mistake. You will take the coefficient directly as 0.15, but it should not be done because 0.15 is for a span of 100 meters. Therefore for 1 meters, the wave effect coefficient will be 0.15 divided by 100, which is 0.0015. So we have to calculate the stress allowing for losses due to friction and wave effect at the following points. Assuming jacking end is A, compute the effective stress at B. If the cable is tensioned from both ends A and B, calculate the minimum stress loss in the cable and its location. Okay, so it's a nice example. So let's start with it. Note down the given data properly. Okay, then so now firstly let us come to the slope of the cable. For first case, as it is jacked at only one end, we get the slope as 4e by L, okay, which comes out to be 0.08. Therefore the angle as it is jacked at one end itself is 2 into multiplied by slope, 2 times of the slope, which comes out as 0.16 radians. So now let's put in the formula for friction, that is P naught into bracket mu alpha plus Kx. Now case 1, when we are solving, that is the loss of prestress between A and B, that is we want to find the stress at end point, that is B. Here anchorage is done at only one end, hence entire length is taken as x, that is x is equal to L is equal to 20 meters. Therefore substituting in the friction formula, P naught is 1000, which is the given stress, substituting value of mu, substituting the value of alpha, that is 2 times of slope, because jacking is done at one end only, we get the answer as 59 Newton per mm square. Therefore when it is a single jacking system at point A, we find that the stress which is lost is 59 Newton per mm square. Therefore effective stress at B will be applied stress 1000 minus 59, which is the loss, which is equal to 941 Newton per mm square. That means as we reach the end B, the loss happening is 59, and hence the stress at point B is 941 Newton per mm square. Then we'll come to case 2. In this case, both side jacking is done, hence the formula for the slope and the cumulative angle changes. Formula for slope remains same, only cumulative angle changes, which is now, in this case your angle will be 0.08, okay, that is equal to the slope itself. Now the thing to note down here is, as we are jacking from both the ends, that is end A as well as end B, the minimum stresses will occur at the center span, that is in this case L is equal to x is equal to L by 2. Now this is the important thing which has to be noted, and alpha we have taken as 0.08, which is the slope itself, 4e by L. Therefore substituting in the equation, we have to put x is equal to L by 2 or 0.5 L, which is 10 meters, and the angle alpha as 0.08. We get the loss as 43 Newton per mm square. Therefore the effective stress at point C, which is the point at which maximum loss is estimated to occur, as jacking is done from both the ends, the C is the center point, we get the effective stress at the center as 1000 minus 43 is equal to 953 Newton per mm square. So we have solved a variety of examples. Tomorrow I might put up a small test or say revision, or we'll have assignment questions which needs to be solved on that day itself. So today I request all of you all to go through the examples properly, make the notes. I know it is not that easy to follow the videos suddenly and understand everything, but if you have doubts, you got to respond back to the teacher, ask the doubts and get it cleared. Otherwise we have to assume that you are understanding everything. So please see that, you know, whatever problems you have, you keep them aside. Because of the situation, no one can help. Okay, everyone is facing the problem. So please, as this is your final semester and this is the thing which will affect your degree, please go through the examples. So only we are putting 2 or 3 examples only per day. Okay, so please go through the examples, and before we conclude this chapter, see that you have covered the chapter. If you have doubts, again I am requesting, please get back to me. Don't keep the doubts with yourself. If you are happily getting the solutions from your friends, well and good, else you are free to text me or call me. So let's conclude today's lecture. Thank you.